The last thing that we're going to do in today's lecture is we're going to solve an example problem involving the first law applied to an open system with unsteady flow. And with that, we will be invoking or using the assumption of the uniform flow process in order to solve the problem. So I'll begin by writing out the problem statement. So with that, what we will do is we will write out the information that we know about the problem. We know that we're dealing with an insulated rigid tank. And when you see insulated, what that implies is that there is no heat transfer. So it would be an adiabatic process, or adiabatic tank, and it is a rigid tank. And the word rigid here is important because that means that the tank walls are not changing, which will come into play as we go through the analysis, because that means that there is no boundary work as part of the process. We're told that the gas that flows in has conditions of atmospheric, so 95 kPa and 17 degrees Celsius. And we're told that originally the tank is evacuated, meaning that it is at 0 kPa, and the final state of the tank is it goes to atmospheric pressure, which in this case is 95 kPa. And what we're told to find is the final tank temperature T2. And we're told to assume the following. We're told to assume constant specific heat. So Cp and Cv are constants. So that's what we know about the problem, the information that has been provided and what we're trying to find. So let's begin with the analysis. What we will be doing is dealing with the first law for open systems and unsteady flow, invoking the assumption of a uniform flow process. So the analysis So that is the equation of the first law. Now what we can do, we can look at the information that we've been given for the problem. First of all, we're told that the tank was insulated, meaning that there's no heat transfer, so the heat transfer term goes to 0. The second thing, we were told that it was a rigid tank, and I had mentioned earlier that means that the walls aren't moving, so there's no opportunity to do work. And so that term goes to 0. And finally, mass is only flowing into the tank. So we only have mass flowing in, there's nothing flowing out. And that means that the term with the exiting mass goes to 0 as well. So with that, we can relatively quickly reduce our first law to something that looks like the following. So that's what our first law looks like. Now the other thing that we were told that it was originally evacuated, meaning that there is no mass in the tank at the beginning, at state 1. And consequently, this term also goes to 0. simplifying it even further. So what we are left with is the following equation for the first law. So we now have to work with this equation, and by studying it for a moment, we can look and say, on the left-hand side we have the mass N, and on the right-hand side we have the mass at state 2. It was originally evacuated, meaning that there is no mass in the tank, so everything that flows in becomes mass at state 2. So from continuity, which is something that you would learn in a fluid mechanics course, we know that mass N is equal to mass 2, and therefore what we can write is Hn is equal to the internal energy at state 2. So that's the equation that we're going to be working with as we go through coming up with a solution to this problem, trying to determine the final temperature at state 2. So the equation that we have, Hn is equal to U2. Now, everything that we've seen thus far have usually been dealing with evaluating the change in either enthalpy or change in internal energy. We haven't been faced with a situation where we need to determine an absolute value for those. So how do we deal with absolute values? Well, in order to do this, what we're going to do is look back when we talked about the definitions for how to calculate either internal energy or enthalpy from the specific heats. And remember, for ideal gases, we said the equations were as follows. So we can integrate these equations now. The values of Cp and Cv, remember we had said in an earlier lecture that they can be functions of temperature. However, for this particular problem, we have been told that the values are constant. There are other gases where Cp is constant, or the specific heats are constant, and these are argon, helium, neon, krypton, xenon. So those are gases where we have a constant. Now we're dealing with air, which normally it wouldn't be a constant, but we're told as part of an approximation for the problem that we should assume that. So what we need to do is we need to integrate this equation from some base state to the point at which we have an interest. And what we're going to say is that at absolute zero, we'll say that both the enthalpy and the internal energy is 0 kilojoules per kilogram. And with that, we can write out the integration that the enthalpy at state 2 is just going to be the specific heat at constant pressure multiplied by the temperature at state 2, and similarly for U2, we can write it as follows. So going back and looking at the equation that we have to work with from the first law and what we just determined based on specific heats, we can use this information and plug the values into that equation and try to come up with a solution. So with that, remember we're trying to determine the final temperature in the tank. And we obtain the ratio of specific heats, which we said was K. And K for air is 1.4. And Ti here, what we will need to do, this needs to be in Kelvin. So with that, we can say that the temperature at the end of our process at state 2 is 406 Kelvin. And that solves the problem. That is also approximately 133 degrees Celsius. So that is the solution to the problem involving the uniform flow process. Thank you very much.